You're watching MyIPS on MyINDY-TV 23, a free educational service provided by Circle City Broadcasting of Indianapolis. Here's what's coming up this hour. Get more information, special announcements, and weekly program schedules online at wishtv.com. And be sure to follow us on Facebook. Here's what's coming up next.
Hi everyone, my name is Mrs. Gradney. I was a teacher in Louisiana Public Schools for 18 years. And when I was teaching, my favorite thing to teach was math. Today we'll be going over Grade 4, Module 5, Lesson 1. Before we get started, let's gather your materials together. Here's what you'll need for this lesson. You'll need 3 strips of paper, and you can easily make that just by cutting some strips from any paper that you have. It can be construction paper or any kind of paper that you have. Just try to make the strips all the same size, but they don't have to be perfect. You'll also need markers or colored pencils or crayons or something like that. And then you'll need paper and pencil. Now, if you can't find all of these materials, that's okay. You can learn as you watch me. Later in the lesson, we'll use this problem set for practice. If you don't have your workbook, you can have someone help you print the problem set from our website, greatminds.org. If you can't print a copy, that's okay too. I'll show it on the screen and you can just use your paper and pencil to answer each question. Let's begin by thinking about what we already know. We can decompose or break apart a number in various ways. And we can use a number bond to show how we decompose numbers. For example, we can decompose the number 3 into 3 parts of 1, 1, and 1. We could also decompose 3 in another way into 2 parts of 1 and 2. Well, let's add some units to that. What if instead of just talking about the number 3, we were talking about 3 cats? We could still decompose 3 cats into 3 groups of 1 cat, and 1 cat. Or we could decompose 3 cats in another way into 2 parts, 1 cat and 2 cats. Well, guess what, guys? When we work with fractional units, they work the same way. We can decompose fractional units in the same way that we decompose whole numbers. So let's try it. Go ahead and grab one of your paper strips. Let's say this strip represents 1 whole. Imagine you have a classmate sitting next to you that you can talk to throughout our time together. Speak out loud to your imaginary classmate and say what number this strip of paper represents. Hopefully you said 1. Now let's decompose or break apart our whole into 3 equal units. I'm going to show you how we can fold our paper strip to make 3 units. So I'm kind of folding this part over and I'm trying to make this part to be about the same size as this part that I can see here. And once I can kind of move it like this, once it kind of looks like it's about even, I will fold it down and crease it. And then I can fold this other part over to make those 3 equal parts. Pause the video if you need more time to fold your strip of paper into 3 equal parts. Okay, now go ahead and open up your strip, and so that we can see those units more clearly, let's draw lines on the creases we made like this. Great, now we can see those 3 units more easily. So, how many equal units are in the whole? Think. Say. There are 3 equal units in the whole. So what is the name of the fractional units? Think. Say. The name of our fractional units is thirds. Let's touch and count our thirds. Touch and count the thirds with me. Ready? 1/3, 2/3, 3/3. Let's draw a number bond to show our whole decomposed into 3 units of 1/3. So we'll draw our whole and decompose that whole into 3 units of 1/3. Pause the video and do that now. Here's what you might have done. I know the whole is 1, and I can decompose it into 1/3, another 1/3, and another 1/3. 3 units of 1/3. Think of an addition sentence now that we could write to describe this decomposition. Starting with 1 equals, think, say. You may have said 1 equals 1/3 plus 1/3 plus 1/3. Again, 3 units of 1/3. Now let's show another way to decompose our whole into thirds. I'm going to shade some of the thirds. Watch how I shade the thirds. Let's see. So I shaded 1/3, and now I'm shading another third. How many thirds did I shade? I shaded 2/3. Shade 2/3 on your paper strip as well. Now, watch how I'm going to change this number sentence. Now I'm grouping, those parentheses show that I'm grouping some of those thirds together. So what new addition sentence could we write that matches the new groups of thirds, starting with, again, 1 equals, think, say. We can write 1 equals 2/3 plus 1/3 because we grouped the thirds in a different way. Now let's use this same strip and let's double the number of units in the whole. So I'm going to show you how we're going to do that. We're going to fold on the creases again, just like we did before, so those same creases. And then we're going to fold it in half. So try to match up that edge there, fold it in half, crease it down. Now open up your strips. How many units are now in the whole? There are 6 equal parts or units in the whole. Let's turn this strip over to the side that we haven't used yet, and let's draw our lines on the creases so that we can see those units better. Like this. Okay. Now, since there are 6 equal units in the whole, what's the name of the unit fraction? Think. Say. Each unit represents 1/6. Let's count our sixths. Touch and count with me. Ready? 1/6, 2/6, 3/6, 4/6, 5/6, 6/6. Great. Let's shade in 5 of these units called sixths. Whisper count as you shade. 1/6, 2/6, 3/6, 4/6, 5/6. Now let's draw a number bond to show 5/6 decomposed into 5 units of 1/6. So we're decomposing 5/6 into 5 units of 1/6. Pause your video now and go ahead and write that number bond. When you're finished drawing your number bond, hit play to continue. So what you drew may be similar to this. We know we're decomposing 5/6. That's the amount we're decomposing or breaking apart. And we can break that into 1/6, another 6th, another 6th, another 6th, and another 6th, or 5 units of 1/6. Now think of an addition sentence that we could write to represent how we decomposed 5/6. Let's start it with 5/6 equals. Pause your video and write the addition number sentence that matches our number bond. And when you're finished writing that addition sentence, please hit play to continue the video. So what did you write? You may have written 5/6 equals 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6. Whew! 5 units of 1/6. Let's show another way to decompose 5/6. Watch what I'm going to do to this number sentence. So I drew in those parentheses so that we could group some of those 6 together. What new addition number sentence could we write to match this new decomposition? Think. Say. We can write 5/6 equals 3/6 plus 2/6. Now let's draw a number bond to match this new addition sentence. Your number bond should look something like this. We're decomposing 5/6 and we're breaking it into 2 parts. One part is 3/6 and the other part of 5/6 is 2/6. Where can we see these parts in our paper strip? Point on your paper strip where we can see 5/6 decomposed into 3/6 and 2/6. I can see the 3/6 here, and I can see another 2/6 here, and together they make 5/6. Let's take a new paper strip now. You can put that other one on the side and grab another paper strip. This paper strip represents one whole. Let's fold it to create 4 equal parts or units. We can easily make 4 parts by first folding our paper strip in half, so match up those edges, increase it, and then just fold it in half again. If you need more time to finish folding your paper strip, please pause the video. Now open up your strip. Let's draw the lines on the creases so that we can more easily see the units that we've created. What is the unit fraction? Think. Say. Since there are 4 equal units in the whole, the unit fraction is 1/4. Now let's shade all of the unit fractions in this whole. Let's shade all of the fourths. Let's whisper count as we shade the fourths in this whole. 1/4, 2/4, 3/4, 4/4. Okay, so here, what do we have shaded? Think. We have 4/4 shaded. Let's grab our last strip. And again, this strip also represents one whole. Let's fold this strip also into 4 equal parts or units, just like we did the last strip. So we'll fold it in half first. Try to match up those edges as best you can. Crease it and then fold it in half again. Okay, now open up the strip and draw the lines on the creases again. Just like this. Now we can easily see those 4 units in the whole. Since there are 4 equal units in the whole, the unit fraction is also what? Think? Say? The unit fraction is 1/4. Let's shade 3 of the fourths on this strip, and let's whisper count as we shade them. Ready? 1/4, 2/4, 3/4. Great. Now let's put the strips side by side. How much is shaded? Think. Are you thinking about the units? You may have noticed that the first strip shows 4/4 shaded and the second strip shows 3/4 shaded. So how many fourths is that in all? Think. Say. There are 7/4 shaded in all. It's just like if this were a group of 4 cats and a group of 3 cats. 4 cats and 3 cats together make 7 cats. Well, here, guys, we've just changed the unit. Now we're talking about fourths. And 4/4 and 3/4 make 7/4. Let's draw a number bond and write an addition number sentence to represent these 2 parts and their sum. Your work may look similar to this. Here we can see that 7/4 is the total. Here, 7/4 is the total. And it's been decomposed into 2 parts. We can see the 2 parts here in the number bond, and we can see the 2 parts here in our addition number sentence. Now, how can 4/4 be renamed? Think. Say. 4/4 can be renamed as 1. Let's draw another number bond, this time renaming 4/4 as 1. Well, I know I can easily just replace that part here with 1. So I know the parts will be 1 and 3/4. But how can I write 7/4 with renaming 4/4 as 1? I can write 7/4 as 1 and 3/4. Let's also write an addition number sentence that represents this number bond, starting with 1 and 3/4 equals. Pause the video to complete this number sentence and hit play when you're done. You may have written 1 and 3/4 equals 1 plus 3/4. With a fraction greater than 1, like 7/4, we can rename it. We can say this is 1 and 3/4. 1 and 3/4 is another way to record the decomposition of 7/4 as 4/4 and 3/4. Think, how are 7/4 and 1 and 3/4 the same, and how are they different? Talk to your imaginary classmate to explain your thoughts. Some of you may have said that 1 and 3/4 has a whole number, but 7/4 doesn't have a whole number. It's just a fraction. You may have also noticed that they're equal fractions because they represent the same amount. So when a fraction is greater than 1, another way we can write it is using a whole number and a fraction. Now we've been using strips, but let's move to tape diagrams. You can set your strips to the side. Look at the tape diagram that I have here. This rectangle represents 1, or 1 whole. What's the unit fraction? Think, say. The unit fraction is 1/5. What fraction of the whole is shaded? Think, say. 2/5 of the whole is shaded. Write an addition number sentence to show how we can decompose 2/5 into unit fractions, starting with 2/5 equals. So what number sentence did you write? Say it. You should have written 2/5 equals 1/5 plus 1/5. Let's look at another tape diagram. This rectangle again represents 1 whole. What's the unit fraction? Think, say. The unit fraction is 1/5. Notice these brackets. Now we're grouping those 1/5 in a different way. Draw the model on your paper, label it, and then write an addition number sentence showing how we decomposed 4/5 as shown by the brackets. Your work may look similar to this. We can see 4/5 is decomposed into 3 parts: 1/5, 1/5, and 2/5. Let's try another one. Take a look at this tape diagram here. What's the unit fraction? Think, say. Some of you might think the unit fraction is 1/6, and some of you might think the unit fraction is 1/5. How can we tell that the unit fraction is actually 1/5 and not 1/6? Speak out loud to explain your thinking to your imaginary classmate. When we're trying to decide what the unit fraction is, we need to pay close attention to how many equal parts make up 1 whole. You may have noticed that on this tape diagram, these 5 units make up 1 whole. So the unit fraction is 1/5. And then there's this extra unit added on. So this tape diagram is actually showing a number greater than 1, or a whole number and a fraction. So what fraction does this tape diagram represent? Think, say. Some of you may have said 6/5, and some of you may have said 1 1/5. If you said either of these, then you're correct. On your paper, write a number sentence showing how we could decompose 6/5 into parts. You can break 6/5 into whatever parts you want. Did you write any of these number sentences? If so, great job. But these aren't the only number sentences we could have written, because there are many ways that we could decompose 6/5 into parts. Now take a look at this number sentence. Think, how could we model this number sentence using a tape diagram? Explain your thinking to your imaginary classmate. You may have said that we should draw a rectangle and partition it into 6 equal units to make 6. We should label the whole thing as 1 because 6/6 is equal to 1 whole. Then we can use brackets to label the parts that are shown in the addition sentence. Your tape diagram may look similar to this one. Oops, move that back down. I labeled the whole thing as one whole because 6/6 is equal to one whole. And then I used the brackets to label the add-ins from the number sentence. So I have 1/6 here, 2/6, and 3/6.
Hi, I'm Mrs. Bell, and I'm going to be engaging you in some fluency practices to help support you in your Eureka Math lessons. Our first fluency practice is called Read Tape Diagrams. Just a reminder, a tape diagram shows a whole broken into parts. The tape diagrams that we're going to be seeing have equal parts. Take a look at the tape diagram on your screen. You will notice I have a tape diagram with a whole equal to 10 broken into 2 equal parts. A division problem we could write to find the value of each unit would be the whole of 10 divided by 2 equal parts gives us a value of 5 for each unit. Now that we know the value of each unit, let's write a repeated addition sentence to represent our whole. 5 plus 5 equals 10. Let's do another together. Say out loud the value of the whole. 6. How many parts is our tape diagram broken into? 2. Let's say our division sentence together. 6 divided by 2 equals 3. Now that we know that each unit represents 3, our repeated addition sentence would be 3 plus 3 equals 6. Take a look at our new tape diagram. What do you notice about the parts? There are 3 parts this time. What's the value of the whole? 15. Let's say our division sentence together. 15 divided by 3 equals 5. Now that we know that each unit has a value of 5, let's write our repeated addition sentence together to find our whole. 5 plus 5 plus 5 equals 15. Let's try another. What's the value of the whole? 6. How many equal parts are we breaking our tape diagram into? 3. A division problem we could write to find the value of each unit would be, did you say 10 divided by 3? I'm sorry, did you say 6 divided by 3 equals 2? What would our repeated addition sentence be? 2 plus 2 plus 2 equals 6. How many parts are we breaking our tape diagram into this time? What's the value of the whole? Say our division sentence. 12 divided by 4 equals 3. Our repeated addition sentence would be 3 plus 3 plus 3 plus 3 equals 12. What's the value of the whole? How many equal parts did we break our tape diagram into? I want you to say out loud what the division problem would be to find the value of each unit. Did you say 24 divided by 4 equals 6? Tell me my repeated addition sentence for the tape diagram. 6 plus 6 plus 6 plus 6 equals 24.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Greeting IPS students. My name is Mr. Schnepp. I am a 5th grade teacher in IPS, and today I'm going to talk about Lesson 1 of your iReady packet. Lesson 1 deals with, on page 4, deals with understanding place value. Now I know all through the course of your school year we've talked about place value, but we're going to take it a little bit deeper today. Okay, I've got a place value chart up here. So the first thing I want to do is I just kind of want to go through and remind you of the spots. So here's our decimal point. So as we go to the left, our numbers get bigger. There's 1, tens, hundreds, thousands, 10,000s, and 100,000s. And I know that you guys have all seen those over and over and over, okay? Then as we go to the right side of the decimal point, the left side are our whole numbers, the right side of the decimal point are our partial numbers. So we have 1/10 or 0 and 1/10. We have 1/100th or 0 and 100th, and we have 1,000th or 0 and 1,000th. So that's the place value chart that you are used to seeing. Okay, so when we want to talk about, what we're going to talk about today is how the numbers increase in the place value chart. And as we move to the right or to the left on the place value chart, as we move to the left, so as you move to the left, the numbers increase by times 10. Okay, so for example, let's take the number 7 and we're going to put it in the ones place. Okay, so as we move to the left, our numbers are increasing, and it increases by times 10. So 7 times 10 equals 70. All right, 70 times 10 equals 700. 700 times 10 equals 7,000. 7,000 times 10 equals 70,000, and 70,000 times 10 equals 700,000. So I just want you to remember, as you move left on the number line, the numbers increase by times 10. As we go left on the number line, okay, so as you move left, or as you move right, numbers decrease by 1/10. Numbers decrease by 1/10. And I know at some point, at least in my school, and I think you have in your school too, when we talk about fractions, fractions are division problems. So actually they decrease by 1/10 or they are divided by 10. Okay, so let's take the same number 7, and we got 7 divided by 10 equals 7/10, and 7/10 divided by 10 equals 7/100, and 7/100 divided by 10 equals 7,000. So before we got into the lesson, I just wanted to give you a quick review of the place value and how they increase by 10 as the numbers get bigger, and they decrease by 10 or 1/10 as the numbers get smaller. We're going to start out and we're going to use a hundreds chart. Okay, and we're going to start out with the number 0.7. Now, so on the hundredths chart, so 0.7 is actually 7/10. Remember, we want to say it by its value and not by the numbers that are there. So we're going to shade in our place value chart, and I'm going to shade in 7/10. The chart is a hundredths chart. Okay, and remember, on a hundredths chart, each column is worth 10. So that is 7/10. We've shaded in 7 columns, and it's tenths because each row has 10 in it. So that is our 7/10. On the other hand, we're going to look at 7/100. Okay? So if each column is worth 10, each square in the chart is going to be worth 100. Okay? So in this case, we're going to shade in 7/100. We're using the number 7 for both of them, but as you can look, it is completely different. We've got almost the whole chart covered in here, and here we only have 7 spaces covered in. Okay, so I want to complete this. So we're going to complete this statement, and the statement that we're going to complete is 0.07 is 1/10 of 0.7. And if we go back up here to where we looked at, we started out with 0.7 or 7/10, and we went to 7/100. And remember, we talked about when we go to the right, we divide by 10, and by moving the decimal point, that changed that. So 7/10 is 1/10 of 7/100. On the other hand, 0 and 7/10 is 10 times, and once again, we use these same numbers, and we have 0 and 7/100 and 0 and 7/10. If we're going this direction, we're going to multiply by 10. Looks like a 6 there. We're going to multiply by 10. All right, and that takes us to 7/10. Okay, so that's using a hundredths chart or a grid to determine place value. Okay, that's one way that we can do it. Okay, another way that we can do this is we can do it by drawing a number line. Okay, and so we're going to get rid of our hundredths chart here, and we're going to put our number line up here. All right. Okay, so and on the number line, we're going to represent the numbers. We're going to draw 0.1 and 1 on the number line, which means we have to divide the number line into how many sections? We have to divide it into 10 sections, okay? So this would be 0, 1/10, 2/10, 3/10, 4/10, 5/10, 6/10, 7/10, 8/10, 9/10, and 10/10 is 1. Okay, so on the number line, we're going to plot 1/10, and we're going to plot 1. So the questions on your worksheet that's going to go along with the number line, they're going to ask you what number you have the multiplier divided by. So 1/10 times 10 equals 1, and 1 divided by 10 equals 1/10. Again, depending on which way you're moving on the number line. So on the number line part of this worksheet, they're going to ask you to use the number line to explain why 1 is 10 times the value of 2/10. Okay, and this is it's very simple. You're just writing a sentence. Okay, and your sentence might look like this. 1 is 10 times the value of 1/10 because 1 is 10 times further than 0. That's simple. That simple. Okay, so just a quick review. Place value, as we move to the left on the number line, our numbers increase. They increase by times 10. As we move right on the number line, our numbers get smaller and they decrease by 1/10 or divided by 10. All right, you can use a grid model to do this. You could use a number line model, and it's just as simple as explaining that it's 10 times, in this question it's 10 times further. Now on your worksheet, you're going to find some problems with different numbers. I didn't use worksheet examples because there's not very many questions on this worksheet. So, thank you for watching today's lesson on place value. We do miss you guys. We hope that you're getting along well and your families are healthy, and hang tough and stay well.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Hi everyone, my name is Miss Bertuman, and I was a teacher in California. Now that I work for Great Minds, we're doing whatever we can to help support building with knowledge on the go. I'm excited to do these next couple of Eureka Math lessons with you. So let's get started. We're going to start today's lesson with Grade 5, Module 5, Lesson 1. Now for this lesson, I'll be using quite a few materials. I'm going to have with me some paper and some pencils. I'll also have centimeter grid paper, and this is one that you can find in your workbook if you have it. It looks just like this. And if you don't worry, you can just watch and learn along as I teach alongside this lesson. The other item that we'll be using is isometric dot paper, again also in your workbook, and it's again okay if you don't have it. But if you do have your workbook, it looks like this. We'll be using also different cubes for this because we'll be doing quite a bit of building with this lesson. And last but certainly not least, I'll also be using the problem set Grade 5, Module 5, Lesson 1. Now that is also in your workbook, and it looks like this. Here's the first page, and here's the second page. So let's go ahead and get started again with Grade 5, Module 5, Lesson 1. So the first thing that I will be doing is going to my grid paper, which you'll see here on the screen. And on this grid paper, I am going to shade in an area of 4 square units. One, two. Now these 4 squares are going to be used as the foundation of our structure. So now I'm going to place 4 cubes directly on top of each shaded square. I want you to think about these 4 cubes as the ground floor of a building. So now we're going to make the second floor by putting another 4 cubes directly on top of them. Now you can see the red cubes make up the second floor, but when I tilt my camera, I have yellow cubes on the first floor. So how many cubes are there now? There are 8 cubes total. So I'm going to now add a third floor. Okay. So we can see that the third floor is made up of 4 green cubes. And when I tilt my camera again, you'll see that the second floor is red and the first floor is yellow. How many cubes are there total now? Say it. 12 cubes total. Now keep in mind that our ground floor consisted of 4 yellow cubes on the bottom. That was our ground floor, and there were only 4. And then instead of building our structure wider, we instead built our structure taller. So when we're counting our cubes, even though we can only see here that there are 4 cubes at the top, we know that this structure is actually consisted of layers. 3 layers to be exact, of 4 cubes each. So if we counted them by the layers, we could see that it would actually be, and if I count, it would be 4, 8, 12. So what we're doing today is we're using these cubes as a unit to measure volume. A volume of a structure, of our solids, which you just saw. And we're measuring with volume the amount of space it takes up. So we call this unit a cubic unit, or we can also call it unit cubed. So just like we use the squares to measure area in square units, we will be using cubes to measure volume in cubic units. So in this case, this one has a volume of 1 cubic unit, or 1 units cubed. And in something like this, we see that it's made up of 2 cubes, and it also has a volume of 2 cubic units, or 2 units cubed. And then of course with something like this, we count 3 cubes, 1, 2, 3, and we see that this has a volume of 3 cubic units. Continuing along, this structure here, similar to what we built earlier, has 4 cubic units, or 4 units cubed, and has a volume of 4 units cubed. But this is just one type. So I'm going to go ahead and move this structure over. I'm going to pull out another 4 cubes. Go ahead and move this so we can see it. This one here also has a volume of 4 units cubed, or 4 cubic units. And the reason being is, even though from the top view level we see 3, this second portion here has a second layer of 1 cube. So it still has a volume of 4 cubic units. So now that we've built the structures using unit cubes, we're going to start drawing them out using this isometric paper. So I'm going to start by choosing my color. And the first thing that I do is I start off by connecting 4 dots to make a parallelogram, like so. I then add another parallelogram that shares those 4 dots, like so, and then another one to the right. And there we have 1 cubic unit. Now I'm going to go ahead and model for you how to do another structure with 2 cubes on the paper. Again, I start off with my parallelogram with the 4 dots, but this time I'm going to make it a little bit larger. So I'll start off here. Notice how I have those 3 dots in a row and 3 dots in a row on the bottom. This serves as the line in the middle. And again, my parallelogram up top. And there we have it, 2 cubic units. Now that I've walked you through that process, I'd like you to go ahead and explore on your own if you have this workbook paper and see if you can make some structures on your own, no more than 10 cubic units. So now that we've finished drawing out some of our structures, I'd like you to delve now into the actual problem set. Again, here it is on the screen. If you need to pause to write out the problems, go ahead and do that now. I'd like you to start off with problem 1, continue through A, B, C, D, E, and F, because we'll definitely be talking about this one during the student debrief. I'd like you to then go into problem 3A and 3B. If you have time, go ahead and jump into problem 2. So in problem 1, you were asked to look at a series of different figures and write in the volume and then the explanation as to how you saw how the figure was built. Maybe you counted the cubic units, or maybe you counted them in a particular way. So looking specifically at figure C and D, go ahead and move myself up here. We have over here, I hope you were able to see that figure C has a volume of 9 cubic units. D also has a volume of 9 cubic units. So with figure C, we can see that there are 3 layers, and each layer has 3 cubes. So the way that I saw it was 3, 6, 9 cubic units. Now with figure D, I was thinking about it in terms of layers, but instead of going from bottom to the top, I was actually counting it. I'm not sure if you were doing the same, but going from left to right. So here I see that there are going to be 4 cubes on the far left-hand side. There's just one that's hidden right over here. But we know it's there because this second layer cannot hold itself up without those 2 cubes being below. So I know that there's going to be 4 cubes here. There's one here in the middle in the second layer, and then an additional 4 cubes to the right. So 4 plus the 1 make 5, plus the other 4 make 9. Volume 9. Again, just as mentioned before, we can see that the volume will take up different space. It's just a matter of how many cubes can fit in that space. Now let's look a little bit closer at problem 3. And the question was, what was Joyce's mistake in problem 3? We see that Joyce thought that by looking at the cubes, there are 5 cubic centimeters, and we have to figure out her mistake. Now, in just looking at this picture here, I can see 1, I see 2, I see 3, I see 4 here, and then 5 is over here in the back. What Joyce isn't seeing is the cube that's directly underneath this first cube here. And again, in thinking about the work that we did earlier, we know that this cube cannot be held up unless there's a cube directly below it. So it's hidden, but we do know it's there based on what we see here on the second level. So Joyce's mistake in problem 3 is that there's not 5 cubic centimeters. There's actually 6. There's just one hidden cube, but we know it's there because it's directly underneath the second layer of this cube right here.
Hi, I'm Ms. LaFont. I was a 5th grade math teacher in Louisiana. Now I work for Great Minds. And while schools are closed, I'll be here doing math fluencies with you. Just know that we're doing everything we can to support your knowledge on the go. Let's go ahead and get started. Our first fluency is coming from Grade 5, Module 5, Lesson 1, and it's called Find the Area. The first thing I'd like for you to do is have a look at this shape here. I'd like for you to think about what is the name of this shape. On my signal, you'll say it. Ready? Perhaps you said a rectangle, which is correct. It could also have been called a parallelogram or a quadrilateral. I'd like for you to write the area now of this shape in a multiplication sentence, starting with the longest side length. Okay, let's check. Our longest side length is 4 inches, and our other one is 2 inches. So our expression could have been 4 inches times 2 inches equals 8 inches squared. Great, let's try another one. Have a look at this shape. What is the name of this shape? On my signal, say it. Hopefully, or maybe you said a square, and that's correct. It could have also been called a rhombus, a quadrilateral, or even a parallelogram, or even a rectangle. What I'd like for you to do now is go ahead and find the area by writing it in a multiplication sentence, starting with the side length shown. Okay, here we go. We see 5 centimeters times 5 centimeters. Because this is a square, we know that the other side must be the same length. So 5 times 5 is 25 centimeters squared. Okay, let's try the next one. We see that this is a rectangle. Go ahead and find the area of this rectangle by writing it in a multiplication sentence, starting with the longer side. Okay, so your sentence should look, let's check, 7 centimeters times 2 centimeters equals 14 centimeters squared. Okay, let's try the next one. Find the area of this shape by writing a multiplication sentence with the side that's written there. Go ahead. Okay, perhaps you wrote 6 inches times 6 inches. We see this is a square, so that gives us 36 inches squared. Okay, let's have a look at this one. Okay, find the area by writing a multiplication sentence, starting with the longer side. Okay, let's check. 5 inches times 3 inches equals 15 inches squared. So the area of this figure is 15 inches squared. Okay, and let's look at our last one. Go ahead and find the area. Write that multiplication sentence, starting with the longer side. Okay, let's check. 11 centimeters times 3 centimeters gives us 33 centimeters squared.
You're watching MyIPS on MyINDY-TV 23, a free educational service provided by Circle City Broadcasting of Indianapolis. Here's what's coming up this hour. Get more information, special announcements, and weekly program schedules online at wishtv.com. And be sure to follow us on Facebook. Here's what's coming up next.
Hello, my name's Mr. Carr, and today we're going to be doing 6th grade math. This lesson is number 1 in your home learning packet, Understanding Ratio Concepts. Let's start with what is a ratio. A ratio is a comparison of two values. We use these every day. You go to the grocery store with mom and bananas are $1 a pound. Pounds of bananas and dollars. You go to the gas station and your car gets miles per gallon. We're comparing miles and gallons. Those are ratios. So, if we were to say that we had 3 circles and 4 squares, what would be the ratio of circles to squares? Well, the order is important in a ratio. Here we have 3 circles and we have 4 squares. Our ratio is 3 circles to 4 squares, 3 to 4. Now, we have 3 ways to write a ratio. Typically, we're going to see a ratio with what's called a colon in between it. We could also write that using the word 2, T-O, 3, 2, 4, or as a fraction with either a horizontal or vertical fraction bar. All of those represent the ratio 3 to 4. In this case, 3 circles and 4 squares. Let's look at one other example. Let's say that Rita collects marbles, and she has 6 purple marbles and 5 red marbles. What is the ratio of red marbles to purple marbles? We've got 5 red, we've got 6 purple. So our ratio there is going to be 5 to 6. But what if I said, what is the ratio of purple marbles to total marbles? Well, it doesn't tell us how many total marbles we have, but we know that we've got 6 purple and 5 red, so we can just add those together, and we have 11 total marbles. So if we say what is the ratio of purple marbles to total marbles, it's 6 to 11. We call that part, whole. 6 purple marbles are part of her collection. 5 red marbles are part of her collection. 11 total marbles, that's the entire collection. Part, and whole. And that, ladies and gentlemen, is an introduction to ratios. Thank you very much.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Hello, my name is Mr. Carr, and today we're going to be learning about 6th grade math. Today's lesson corresponds to lesson 2 in your home learning packet, Rate Concepts. What is a rate? Well, a rate is a specific type of ratio where two quantities are being compared using different terms. What does that mean? Well, if we're comparing red marbles and blue marbles, we're comparing marbles, same term. But if we're comparing miles per gallon, we're comparing miles and gallons. Days in a week. The cost of bananas per pound, dollars and pounds. Those are ratios where our two quantities are being measured using different units or terms. Units or terms, we can use those phrases interchangeably. Let's do a couple examples. Let's say that Jim, being a good Samaritan, can make 8 donuts in 40 minutes. And Gail, also being a good Samaritan, takes 18 minutes to make 3 donuts. Who makes donuts faster? Well, in this situation, it's tough to compare. But we can concentrate on Jim first. He's making 8 donuts. How long does it take him to make 1 donut? Well, to find that out, we would need to take our 8 donuts and split them into 8 parts. Each of those parts would be worth 1 donut. We split things apart mathematically using division. 8 divided by 8 is 1. If we split our donuts into 8 parts, we're going to need to split our minutes into 8 parts. And each of those 8 groups will correspond with a donut. 40 divided by 8 is going to give us 5, which means that Jim takes 5 minutes to make 1 donut. Now, if we look at Gail, 3 donuts, 18 minutes. We want to know how long it takes to make 1 donut, so we're going to divide 3 by 3. We'll get 1. 18 divided by 3 gives us 6. It takes Gail 6 minutes to create 1 donut. Not quite as fast as Jim, but we don't have to hold it against her. All right, let's say that Gina is filling up her swimming pool. It's getting to be nice out. We've been stuck at home. Let's get the pool filled up. She puts a hose in there, and the hose emits, lets out, spills 56 gallons every 9 minutes. What is the rate that the hose is emitting water, gallons and minutes here, in terms of gallons to minutes and minutes to gallons? Let's remember that the order always matters in ratios. Well, we've got 9 minutes. So if we want to find out how much for 1 minute, we're going to divide by 9. 9 divided by 1 is 1. That's minutes. So we've got 1 minute. That's minutes over here on the other side. 1 minute. Now I've got gallons, 56 gallons. Well, we split our minutes into 9 pieces. We're going to split our gallons into the same 9 pieces. 56 divided by 9 is going to be 6. That should be a 54, by the way. And 54 divided by 9 is 6. Gallons to minutes, 6 gallons for every 1 minute. Minutes to gallons, we have to reverse the numbers. We reverse our terms. 1 stays with minutes, 6 stays with gallons. The order matters. Let's do one more. We're going to use something called a double number line. Lucky and Dot are going on vacation. They drive 162 miles. It takes them 3 hours. How far can they drive? In 5 hours at the same rate. All right, the way a double number line works, just like it sounds, there's two number lines. So let's start with that. Our number line should be the same length. One number line is going to measure miles, while the other number line is going to measure hours. If we start right here, we have 162 miles. We start at 0 always. We go from 0 hours to 3 hours. Well, we can cut this into 3 pieces. It's a number line. So there's going to be 1 and there's going to be 2. Now we can already see those line up. In 3 hours, we're going to go 162 miles. So let's split, we split our 3 into 3 pieces. Let's split 162 into 3 pieces. I get 54 when I do that. So this would be a 54. We're counting by 54s, right? 0 plus 54 is 54. 54 plus 54. 108 plus 54 is 162. Now, I can see that in 1 hour, Lucky and Dot traveled 54 miles. We want to know how far they can go in 5 hours. Well, 1 hour. Every time they do 1 hour, they're going 54 miles. They're going to do that 5 times, which means they're going to go 54 miles 5 times. And 5 times 54 is 270 miles. When you're making your double number line, remember, know your 2 units, miles and hours. We always start at 0. Know what your total is. We started with 3 hours and 162 miles. They're going to line up. They're equivalent in this case. And then break into as many pieces as you're going to need. We divided 3 by 3. So we do the same thing to 162. And now we line up at 1 hour, at 2 hours, and at 3 hours. And once we know how far they can go in 1 hour, we can figure out how far they go in any amount of hours. If I want to know how far in 7 hours, 7 times 1, 7 times 54. 17 hours, 18 hours, it's all there. And that is a rate concept. Thank you very much.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
My name is Mr. Carr. Today's lesson is on 6th grade math. It corresponds to lesson 3 in your home learning packet. Today, we're learning about unit rates and equivalent ratios. What is a unit rate? Well, we learned yesterday that a rate is a comparison of 2 quantities using different terms, miles per gallon, dollars per pound. A unit rate is a comparison of 2 values where one of the values is 1. What does that mean? 25 miles per gallon. $5 for 1 pound of avocados. We have a 1. Remember that per means for every. You're going to see this a lot, and a lot of times students say, well, I don't know, that's only 25. There's not a second number there. Per means for every, for 1. So this is 25 miles for 1 gallon. All right? That is a unit rate. Let's look at some examples. one thing I always like to remember is that a unit rate answers the question how much for one? How much for one? All right, let's start with Tim. Tim's a reader, and Tim can read 5 books in 40 hours. How long does it take Tim to read 1 book? Well, that's going to be a unit rate because we're going to have a comparison of 2 values, books and hours, where one of our units is 1. How much for 1? And we want to know how long it takes him to read 1 book. So we're going to have a unit rate in terms of books. Well, to get to 1 book, we know we've got to divide by 5. We want to know 1 book, we've got to split 5 into 5 pieces. We split things into pieces mathematically using division. 5 divided by 1 is 5, but 5 divided by 5 is 1. So we have 1 book. Then we have to take 40 and divide it by 5. We're going to get 8. And we know that it takes Tim 8 hours to read 1 book. So how long would it take him to read 7 books? Well, that's 1 book. There's another, and another, and another, another, and another, and another, and I think that's 7. 1, 2, 3, 4, 5, 6, 7. There's 7 books. 1 plus 1 is 2, 3, 4, 5, 6, 7. 7 books. How many hours? Well, 8 plus 8, 16, 24, 32, 40, 48, 56. It will take Tim 56 hours to read 7 books. Now, we know that multiplication is just repeated addition, so we could add those up. We could also multiply. It's a lot quicker. 8 times 7, 56. 1 times 7, 7. And where did we get our 7? We wanted to know 7 books, so we multiplied 7 by books to get 7. All right, let's do another one. A teacher bought 200 calculators for $1,040. $1,400. Teacher bought 200 calculators $1,400. All right. At this rate, how much would 60 calculators cost? Well, I don't know how to get to 60, but I bet we can figure out how much 1 calculator cost. We've got 200 calculators here, so we're going to have to split it into 200 pieces. That's division. 200 divided by 200 gives us 1 calculator. 1,400 divided by the same 200 is going to give us 7. 1 calculator costs $7. 1 calculator costs $7. How much would 60 calculators cost? Well, we could add 1 up 60 times, and we could add 7 up 60 times, or we could just multiply. 1 times 60 is going to give us 60. 7 times 60 is going to give us 420. 60 calculators would cost this kind-hearted teacher $420. Let's do one more. A jet flies 1,650 miles in 3 hours. miles in 3 hours. Comparing two different terms, we have a rate. We want to know how long, actually we want to know how far. How far can this jet travel in 8 hours? Well, again, I know how far it goes in 3 hours. If I doubled that, it would be 6 hours. If I did 3 more hours, that would be up to 9 hours. That doesn't help me figure out 8 hours. So why don't we figure out how far this jet can travel in 1 hour? We've got 3 hours there, so we're going to divide by 3. 3 divided by 3 is 1. Now we have to take our miles and split that into 3 pieces. And when I take 1,650 and cut it into 3 equal pieces, I'm going to get 550. We want to know how far it flies in 8 hours. That's 1 hour. And this is miles. So we could do 1 8 times and 558 times, or we could multiply. 1 times 8 gives us 8 hours. And what would our distance be? Well, it would be 8 times 550. In 8 hours, our jet's going to fly 4,400 miles. That, ladies and gentlemen, is unit rates. Thank you.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Hi, my name is Mrs. Meadows. I have been teaching mathematics for 17 years now. Now I'm at Great Minds and I'm looking forward to teaching you the lessons in this course. Today we will be covering Grade 6, Module 4, Lesson 1. We will evaluate identities and build and clarify the relationship of addition and subtraction. This work will lay the foundation for your work later in the module when you solve one-step equations. Today, you will need your student work pages for Lesson 1 and 10 squares. If you don't have any of these materials, it's okay. Just follow along on the screen. We're going to start by drawing a tape diagram to represent the following expression. 5 plus 4. Great. Let's review the answer. This tape diagram represents the expression 5 plus 4. 5, the first part, is represented by 5 blue squares. 4, the second part, is represented by 4 red squares. So this tape diagram, when put together, represents 5 plus 4. Write an expression for this tape diagram. Your answer for this tape diagram should have been 2 plus 2. This expression represents the tape diagram because the first 2 blue squares are representing the first part of the expression and 2 red squares represents the second part of the expression. Write an expression for this tape diagram. The expression that represents this tape diagram is 3 plus 4. 3 is represented by the first 3 blue squares in the tape diagram, and 4 is represented by 4 red squares in the tape diagram. If each of the squares represents 1 unit, represent the number 3 using the squares. Let's review the answer. Add 2 more squares to your tape diagram. Write an expression to represent how we created a tape diagram with 5 squares. 3 plus 2 is the expression that represents this tape diagram. 3 represents the first 3 blue squares, and 2 represents the second part of 2 red squares. Remove 2 squares from your tape diagram. Alter the original expression 3 plus 2 to create an expression that represents what we did with the tape diagram. If you wrote 3 plus 2 minus 2, you are correct. Now we're going to evaluate the expression. 3 plus 2 minus 2 is 3. Let's start a new tape diagram. This time, create a tape diagram with 6 squares. We have 6 blue squares. Use your squares now to demonstrate the expression of 6 plus 4. Now we've added on 4 additional red squares. Now remove 4 squares from your tape diagram. 1, 2, 3, 4. Alter the expression 6 plus 4 to create an expression to represent the tape diagram. If you wrote 6 plus 4 minus 4, you have the correct expression.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Hello there, scholars. I'm Sarah Couch, and I will be working through Grade 7 Math Lesson 1 with you today. The topic is going to be understanding addition with negative numbers. I just want to give you a couple reminders before we move on. A negative number is a number that is less than 0, okay? And it's represented with a minus symbol in front of it, okay? Any number greater than 0 is going to be a positive number, and it's just represented like this. There's no fancy symbols that need to go in front of it. And then 0 actually is not positive or negative because 0 equals no value. If you have $0, you don't have any cash on hand to get anything you want. So that has no value, so it can be neither positive or negative. All right, guys, so let's look at problem number 1 on page 3. It reads, between the time Eco woke up and lunchtime, the temperature rose by 11 degrees. Then by the time he went to bed, the temperature dropped by 14 degrees. The first thing it asks us to do is write an addition expression for the temperature relative to when Eco woke up. So first thing I want you to do is on your paper, I want you to circle 2 phrases for me. I want you to circle the phrase rose by 11 degrees. And then I want you to circle the phrase, dropped by 14. All right, so just circle these phrases in your math problem. And this is important because we need to think about the context of this. So we're going to draw a quick diagram, all right? So this line is going to be the temperature at wake up. Okay, we don't know what it is. It didn't tell us in the story, so it's, we'll just call it A. All right, and so from the time he woke up to the lunchtime, it rose, which means the temperature went up 11 degrees. Okay, and then at lunchtime to bedtime, it dropped or went down 14 degrees. All right, and so this is B, or temp at bedtime. Okay, so what's important to know is that this number is going to be represented with a negative symbol in front of it because it is going down in value. This is increasing in value, making it a positive value, and this is decreasing in value, making it a negative value. Okay? So to write this in an addition expression, we have to think about where we started. So obviously we don't have A, so we can't start there. We're going to start with our positive 11. We don't need to put any symbolage in front of it because it is just positive 11, and that's how it's represented. Now we need to think about that drop, and they want it to be addition, so that is the symbol we have to use. So in order to add this, we need to add it as the negative value. Make sure to use your parentheses. Make sure the reader knows that this is 11 plus negative 14. Go ahead and take a moment to write that on your paper. All right, so next on problem 1, it's asking us to draw a model using integer chips and making 0 pairs. So what that means is we're going to represent our two numbers, our 11 and our negative 14, using chips that represent certain values. So this is a positive 11, so the chips are all going to be positive plus signs, and I'm going to need 11 of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And excuse my smudging, but I'm not going to fix it. Okay, so that means that for negative 14, we're not going to be using positive symbols. We're going to be using our negative symbols, and we're going to need 14 of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so your paper should look something like this, and now we're going to make our 0 pairs. So when you make a 0 pair, you think of putting a positive and a negative together. It's like taking a step forward and then taking a step back. They kind of cancel each other out. So we're going to circle 1 pair here, 1 pair here. And as you can tell, we're going to have pairs for about 11 of these. 3, 4, 5, 6, 7, whoop. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so these are all canceled out. They don't count, okay? So that helps us answer the next question, which is what is the value of the remaining integer chips after the 0 pairs are removed? So after all these guys are removed, boom. How many do we have left over? 3 of the negative chips, leaving our answer to be negative 3. The final question for number 1 asks, what is the net change in the temperature relative to when Eco woke up? So the net change is just the difference from the start and the beginning. So if you remember our little drawing, right? We had the start here, and we had the end here. The net change, right, is that change that happened right here between the start and the end, okay? So that means that when we rose 11 and we dropped 14, our net change actually resulted in a drop or a negative 3-degree drop in temperature. So go ahead and write that on your paper, and we'll move on to number 2. Okay, so let's move on to number 2. It reads, complete the number line model to find negative 5 plus 6. All right, so let's go ahead and write our value up at the top, that way we don't forget. Then we're going to use a number line. And number line is actually my favorite way to work out these problems because it really helps me visualize the sentence. So give me a moment to draw a big old number line. It's not going to be perfect, but that doesn't matter as long as you okay, 1, 2, 3, 4, 5, 6, 2, 6, 1, 2, 3, 4, 5, 6. Okay, negative 2, negative 4, negative 6. All right, so there's my number line. It's not pretty, but it works. So let's look at our math sentence. Where do we start? We always read from left to right, just like we do with a sentence, and a math sentence is no different. So we start at the left with our first value of negative 5. So that's going to give us our starting point. I'm going to go over 1, 2, 3, 4, 5. Just make sure this is where I'm going to start. Okay, easy. The next part, we're going to add. All right, so when we are going to increase in a value, we're going to go to the right on our number line. So we're going to go to the right 6 times. We're going to go 1, 2, 3, 4, 5, 6. That's going to land us right here at what value, kids? 1. So kids, that leaves us with our answer of -5 plus 6, which equals 1. Go ahead and write that on your page real quick before we move on to the next part of our question 2. All right, guys, so the next part says, how would the number line model be different if you wanted to find -5 plus -6? Okay, so we're still adding, right? But now instead of adding a +6, we're going to be adding a -6. So we need to look at that a little bit differently. So our starting point is going to be the same. We're going to be at -5, right? We're going to be adding, but we're going to be adding a negative number, which means our value is going to decrease, meaning it's going to go to the left. So as you can tell, I need a little bit more space over here, all right? So I'm going to pretend I made this all the way over here, and I'm going to make my 6 jumps. So 1, 2, 3, 4, 5, 6, all right? And when I do that, I go from -5, -6, -7, -8, -9, -10, -11. That's where I'm going to land. That is not the same as our first answer for -5 plus +6, which was 1, right? They're not the same. So a possible answer could be that you would start the same way, but then you would end up going a different direction because the second value is different, right? Take a moment, make sure you write a full sentence with a period at the end and a capitalization at the beginning of your sentence to help explain your reasoning for this problem.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Hello there, scholars. I'm Sarah Couch, and I'm going to be working with grade 7, lesson 2 with you today. So today's concept is going to be on understanding subtraction with negative numbers. And if you were able to join me for the last lesson, you're going to have quite a bit of background knowledge to bring with you to this one. So I wonder if subtraction with negative numbers is going to be anything like addition with negative numbers. We will test that out by working through the first couple problems together, and then you guys will be left to do the rest on your own. All right, so the first problem is a story that says Mary takes 9 grapes from Rowan and then decides to give 4 back. Well, how nice of Mary, after taking the 9, to be merciful and give the 4 back. So it tells us to write a subtraction problem to describe how many grapes Rowan has. So we don't know how many he started with, right? All we know is that Mary took 9 from him. So he started out with a -9, right? Because if he only had those 9 grapes, she took them all away. He is out 9 grapes, right? And then it's got to be a subtraction problem. So we need to think, what is being taken away? Because Mary decided to give them back, but we got to think of this as a takeaway problem. So you could think of it like Rowan took 4 grapes back, meaning that from Mary's perspective, they were taking those 4 grapes back, which means that our problem is going to look like this: -9 minus -4, meaning that Rowan got 9 taken away, but then he took -4 of those -9 away from Mary. So good for him. All right, so then we need to draw a model for the subtraction problem using the integer chips. So we've used the integer chips before, just like in our first lesson. I'm going to go ahead and just leave this on the board, and I'm going to write my picture over here. So a couple of differences. We are not adding, right? So that might make our picture look a little different. And we have a -9 and a -4. We don't have any positive values here. So we're not going to use any positive chips, so we'll see what happens. All right, so first, left to right, just like a sentence, -9. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? This represents those 9 little grapes that were taken away from Rowan by Mary, all right? And then Rowan said, hey, give me those things back. He got 4 of them back, thankfully. So from the 9 that were originally taken, we need to mark out 4, right? Because he got them back technically. Right? So now what is he left with, right? The story is that Mary still took 5 of those grapes, meaning that our answer is going to be -5. All right, so how many negative integer chips did you cross out? We crossed out 4. So go ahead and write that down on that first line underneath the picture. And then on the second line, write the subtraction as addition. Well, if you think about it, if we went from -9 on a number line, right, and this is 0, right, -5 is actually going to be somewhere in here, which means we had to go this way, which means we're actually adding those 4, right? Negative times negative, positive, in case you don't know that. So -9 plus 4 is how we'd write that as an addition problem. Go ahead and take a moment to write those down. All right, so the next thing on our problem says draw a model for the addition problem using integer chips. So we just wrote this addition problem, took a moment to write it on our paper, and now we need to draw the model using the integer chips. So left to right, first value, -9. 1, 2, 3, 5, 6, 7, 8, 9. Okay, so if you can recall really quickly from the last problem, I keep stepping way too far off, but it's all right. We had -4, so that meant we canceled out 4 of these negative chips. But it is different now because we are actually adding positives, okay, and we're going to be making our 0 pairs. So I have 1, 2, 3, 4. So let's make our 0 pairs real quick. So this positive can match with this negative, right, and cancel each other out. This positive can match with this negative, cancel each other out. This positive guy can go over here, cancel these guys out. This guy can meet up with this one, and they cancel each other out. So that means that we have this amount left, okay? And what is that value? 1, 2, 3, 4, 5 negative chips, which results in our answer being -5. Now that's interesting because that looks just like our answer from the prior one. So when it asks us how do the 2 integer chip models show that -9 minus -4 is the same as -9 plus 4, we need to think about 2 things. We need to think about our starting point. They both started at -9, right? Now the difference is that we added a +4, and then on the other one we subtracted a -4. But the interesting thing is that we ended up with the same result because we still eliminated 4 negative integer chips. We just did it 2 different ways. So instead of adding 4 positives and canceling out some of those negatives, in one, we just took away the negatives entirely, but we ended up with the same result. The final question for that problem asks, what is the change in the number of grapes Rowan has? Right? What's the change? -5. -5. So on that bottom line, on page 5, go ahead and write -5 and stay tuned. So we are going to start working on problem number 2, which is on page number 6 in your packet. Go ahead and take a moment to open that up and I will read the problem to you. Jin is 3 floors above ground level in a hotel. Leela is on a parking level of the hotel that is 4 levels below ground level. How many floors apart are they? Draw a number line to show 3 minus -4. Don't forget your parentheses. That way you can read it nice and clear. Okay, so I went ahead and drew my number line, and I want you guys to pay attention because right here I put my 0 all the way on the left. Normally I don't do that. Normally I put my 0 somewhere in the middle, but because we're talking in context of a hotel and this being ground level, we're going to start with our 0 all the way over here. Okay, this might seem a little confusing to you, so just stick with me and I promise you we'll figure it out together. So let's look at our math sentence, always starting on the left, just like we should. We have a +3, okay, so 1, 2, 3, I'm going to start right here, okay? So from ground level to here, this is Jin, okay? So we're not thinking about the distance from ground level. We're thinking of the distance between Jen and Leela. Okay, so actually this -4 is not going to be going this way, right? It's going to be going this way. 1, 2, 3, 4. Okay, and this is Leela's distance. All right, so just to be clear, in the story it can be a little confusing because you see that it's below ground level, you want to go to the left, but actually you're thinking about the distance between the two people, and it actually is going to go to the right. So we have Jen's distance of 3, and then we have Leela's distance of ultimately 4, positive, right? Because we increased in value. So 3 plus 4 equals 7, right? And in the context of the floors, they are 7 floors apart. Okay, so these answers are spread out through the problem. So it asks you right below the model, it says, what is 3 minus -4, right? So 3 minus -4 equals 7. Go ahead and write that on your paper. It's that simple. And the next part says, what is the meaning of this answer in the context of the problem? Okay, so what does this mean, right? We're talking about floors. So that means that, I'll write it up over here. Jen and Leela are 7 floors apart. And go ahead and take a moment to write that. All right, guys, so let's go ahead and round off this lesson by looking at number 3 on page 6 together. It says the variables a and b represent positive numbers. When you find the difference, a minus -b, do you expect the results to be less or greater than a? What if a is negative and b is positive? So let's explain. So let's think about this by just looking at the variables, okay? So we have a, positive. We're taking away a negative number. Now, what does that mean to take away a negative number? So let's think about this sentence for a moment, a minus -b. So when you think of taking away a negative number, right, let's think back to Mary and the grapes, Jen and Leela and their floor distance, right? We weren't actually taking those things out of the problem entirely. We were actually taking away the takeaway, right? We were canceling out the subtraction entirely, meaning that this can actually turn into this sentence, a plus b, right? And when we add a value, whether it be positive or negative here, it's not going to matter, right? Because we're always going to increase a value because we are adding. All right, so make sure to take a moment to answer number 3 with your full thought. Begin your sentence with a capital letter, end it with a period, and take the moment to really think it out. If you have any questions or concerns, please reach out to your teachers. We are here for you.
This is MyIPS on MyINDY-TV 23. Here's what's coming up next.
Good morning, scholars. This is Sarah Couch, and I'm going to be working through lesson 3 for grade 7 math in your packets, page 7 and 8. The topic is going to be understanding multiplication with negative integers. So we've been working with adding and subtracting positive and negative integers, and now we're going to be working on multiplication. So what happens when we multiply negative numbers? How can we make sense of it? In order for us to try and make sense of multiplying these negative numbers, let's use something that you might be more familiar with called the distributive property. So let's take a problem. We'll do 2 times the quantity. We'll do 4, and then we're going to add a -4, right? Because we're going to test the theory of multiplying our positives, which we know, and then multiplying our negatives. Wonder what's going to happen there. So this mathematical sentence states that this has to be equal, right? We're going to distribute it out. But you could also add these two numbers together in the middle, and a 4 plus a -4 cancel each other out, making it a 0, which is 2 times 0, which equals 0. Okay, so that answer right there is going to help us know what to do for this negative number. So first thing we're going to do what we know how to do, and we're going to distribute this 2 times the 4. It's positive. We know how to do that. 2 times 4 is 8, right? And then we can distribute this out, but I don't quite know what that's going to look like yet, so I'm just going to leave it like this, right? And then I know that it needs to equal 0, right? So we need to figure out what this is going to represent in order for this mathematical sentence to ring true. So we know that this positive 8, we need to add it to some sort of number here in order to equal 0. Well, how much do we need to add to 8 to get to 0, right? So if we need to, we can use a number line real quick. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so we have 8 here, right? This is our starting point. We have to get all the way over here, right? So that means that we have to take 1, 2, 3, 4, 5, 6, 7, 8 jumps in this direction, right? And if you remember your conversation on number lines, when things are going this direction, they are a negative value, right? Because they are decreasing the value of your integer. So that means that you have to add a negative 8 in order to make this true, right? 8 plus negative 8 equals 0. And that is exactly right. That means that when we multiply this positive integer by this negative integer, our number is going to result in being negative. All right, guys, so we talked about what happens when we multiplied a positive number times a negative number, right? We had A times negative B, right? We knew that was going to be negative C, and even if these switched, if this was negative, this was positive, C would still be negative, right? Let me go ahead and block that off so I don't erase it later. But what about when we run into a situation where we multiply two negatives together? So you can see I set up a similar problem as to the first, but a couple of differences. This is now a negative 2 instead of a positive 2. And I went ahead and wrote the 0 here because we already discussed that these two add up to 0, multiplied by this, making it a 0, that order to make this sentence true. So let's go ahead and distribute. So I know that negative 2 times negative 4, or negative 2 times positive 4 is going to be a negative number, right? And I already know that 2 times 4 is 8, so I'm going to have a negative 8 here. I do not know what negative 2 times negative 4 is. I haven't figured that out yet, so I'm just going to write them over here, right? And then we have 0. So just like last time, we have to use our reasoning skills to figure out negative 8 plus what equals 0, right? So we could still do our number line over here. I'm going to put 0 over here. 1, 2, 3, 4, 5, 6, 7, 8. Negative 8, right? So we have to start here and make it all the way over here. So that means we need to do 1, 2, 3, 4, 5, 6, 7, 8 jumps in this direction, right? That is the opposite direction that we were going the last time. So instead of decreasing in value, we will be increasing, meaning that this number needs to be positive, has to be positive to make mathematical sense. So that means we have negative 8 plus a positive 8, which equals 0, which is exactly true, meaning that when we have two negative numbers multiplied next to each other, it actually results in a positive integer. Now we're going to use this knowledge to help us figure out the rest of the page. So go ahead and get your pencils ready and get ready to solve some problems. So I am not going to do every single one of these. Number 1 says, find each product, then describe any patterns you notice. So I'm going to do every other one with you. So I'm going to label them. Number 1 is going to be 3 times negative 7. And then I'm not going to do number 2. I'm going to do number 3 with you. And that is 1 times negative 7. And then not number 4, but number 5. Which is negative 1 times negative 7. And then 7. Negative 3 times negative 7. All right, guys, so we're going to use a couple of different pieces of background knowledge in order to help us answer it. Now, we just talked about this, so this is new knowledge. This is stuff we just went over. But if you see, if we take out these negative integers, right? It's basically just simple multiplication of 1 digit by 1 digit. So we can do that pretty easily. What we just have to remember is this rule over here. If we have 1 negative, our answer has to be negative, and if we are multiplying 2 negatives, our answer has to be positive. So the first thing I like to do with these is to work to determine, is it going to be positive or negative? So positive, 1 negative, negative, right? So then I know 3 times 7, you can count 3 groups of 7, 7 groups of 3. You can add 3 7 times. There's lots of ways. Or if you just remember that 3 times 7 is 21, you'll remember that this answer is actually negative 21 because we had that 1 negative integer there. Number 3, same thing. We only have 1 negative, so our answer has to be negative. And then any number times 1 is itself. So if we're multiplying that 7 by the 1, our answer has to be negative 7. So we know that it's going to be 7, right? Because we just did 7 times 1 over here. We're going to do 1 times 7, right? Those are interchangeable. Order doesn't matter with those. So we know our answer is going to be 7, but is it going to be positive or negative? Well, we have a negative here, and we have a second negative. So if we look over at our rules, we see that it's actually going to result in a positive. So we do not have to put a positive symbol in front of these numbers. These are just regular integers that we normally work with. So we do not have to put any symbol in front of it. It's just 7. So then we have negative 3 times negative 7. We know that it's going to be positive, right? Oh, and look, 3 times 7, 3 times 7. We know that it's going to be 21. All right, guys, take a couple moments and solve the even problems on your own. Welcome back, everybody. All right, so next we're going to look at problem set number 2, which asks us to solve each problem and explain how you determine the sign of the products. But I wanted you to notice something on those. We have more than 2 products, right? Here in our little math sentences that we know to be true, we only have these 2 integers, right? So what happens when we have more than 2? So let's go ahead and explore that really quickly. So we notice a couple of things. When we only have 1 negative here, we have to have negative, right? But when we have 2 negatives, they kind of like combine together, cancel each other out if you want to think about it that way, and make it positive. So how many negatives are you going to need in order to make a positive? 2. So we have a negative, negative, positive. These 2 negatives combine together and they cancel each other out, right? And this is positive, so it's not going to mess with anything. So this one has to be positive. Now this one, we have positive, negative, negative, negative. So these 2 cancel each other out, make positive, right? This guy, positive, positive. But then we have this lonely negative. He doesn't have another negative to pair it with. So that means that our answer has to be negative, right? And then we have this guy down here, negative 3, negative, blah, blah, blah. All right. So we have a negative, a negative, a negative, a negative, right? And we can make pairs of all of them, right? We'll go ahead and just make it pretty like that. So now we have 2 positives, right? So that means that our answer is actually going to be positive. So what is something that we can notice from looking at these patterns? We need 2's, right? Multiples of 2. Multiples of 2. Even numbers, right? All even numbers are multiples of 2. Odds cannot be divided by 2. And that can help us determine positive or negative rather quickly, right? So if we have an even number of negative numbers in our math sentence, we know it's going to be positive, right? Even. And this is odd, right? We have this lonely guy hanging out right here. He cannot pair up with somebody, therefore we're resulting in a negative answer. And then right here, 2 sets of 2, even, positive. So let's go ahead and utilize this knowledge to help you complete page number 7.
You've been watching MyIPS on MyINDY-TV 23, a free educational service provided by Circle City Broadcasting of Indianapolis. MyIPS airs weekday mornings from 8 a.m. to 10 a.m. For more information, special announcements, and the weekly program schedule, go to wishtv.com. You can also follow us on Facebook.